in today's class, let us understand what are Boolean function. So first let us see what is a Boolean function. Later we will see the simplification of Boolean function, and then at last let us understand so how to take the complement of a Boolean function. Okay. Yes. So Boolean function. Boolean function can be defined as an expression which is consisting of variables, Boolean variables, so which can have either 0 or 1 as values, okay, and operators, Boolean operators, so either plus or dot, that is and or operation, sometimes not operation also, okay. So or operation, and operation, and not operation, and along with this it will be having parenthesis and an equal sign. So it is a expression, it is an expression, Boolean function is an expression which is consisting of the Boolean variables, so which can have either 0 as 1 as the value, and the operators such as and operator, or operator, and not operator, or okay, it can have any of these three operations, and along with that it will be having parenthesis and an equal sign. So that expression is called as Boolean function. Okay. Yes. Now let us consider an example of Boolean function, so which is given by x, y, z dash. Let us consider f. Okay, it's a Boolean function which is having an equation, okay, x, y, and z dash. Now Boolean function, so whatever we write, so even this can have only two values, that is 0 or 1. So this expression or this function can also be derived from the truth table. So the truth table will be consisting of 2 power n rows, 2 power n in the sense, so n is nothing but number of variables. In this Boolean function whatever I have considered, so we have 3 variables. So using these 3 variables we can construct a truth table consisting of 8 rows, 2 power 3, okay, 8 rows. Yes. Now let us write the truth table for this function. X, y, z are the variables. F, let me, okay, so consider this as f1, okay, the first function. So the combination possible are 0, 0, 0 to 0, sorry, 1, 1, 1. So 1, 2, 3, 4, 5, okay, 6, 7. So these are the 8 possible combinations we can have. Now, so if you observe this, so the operation what we have between these variables is AND operation, and you can observe, so one of the variable is in its complement. Therefore, so whenever we have x is equal to 1, okay, and y is equal to 1 and z is equal to 0, so we will have logic 1 for the function. For all other combinations the output is equal to 0. So where do we have x, y, z dash, that is x is 1, y is 1 and z is 0. So that is okay. So the combination is here. Therefore, so for this we will be having logic 1. For all other combination, okay, we need to write logic 0. This is the truth table, okay, we have for the function f1. So now let us consider few more example and let us understand. Yes. So now I have taken 3 more examples. So f2, the expression for f2 we have is x or y dash z. Therefore, so for that function, so if I want to write the truth table, so we have to look into the expression carefully. We have x or y dash z. Therefore, whenever x is 1, so we will be having the function value as 1, and for y dash z also we will be having the function value as 1. So first let me consider whenever, okay, we have x value as 1, so that is for last 4 combination, so the output will be 1, and for another, okay, value, that is y dash z. So in this case x can be anything, so x can be x dash or x can be x. Therefore we need to find out, so where we have y dash z. Y dash z is 0, 1. So 0, 1 combination, where do we have? So we have 0, 1 here, okay, and we have 0, 1 here. So for this, so we have already written 1. Therefore, so in one more place where I need to write 1, logic 1 for the function f2 is here. So x value can be anything and y value must be 0, z value must be 1. So that combination we have in 2 places, okay. But since I have written logic 1 for all the values, okay, of x where we have 1. So for all the rows, okay, for all the rows where we have x value as 1. So this is excluded. Only another place where we need to write the logic 1 is this one, okay. Yes, for all other places we need to write 0. So this is f2. Next is f3. So f3, what do we have? f3, so we have x dash y dash z. Let us find out where do we have x dash y dash z. So that is 0 0 1. So 0 0 1 is here. Next we have x dash y z. X dash is 0 1 1. 0 1 1 is here. So here we need to write 1, and next we need to identify where we have to write logic 1 for the last term what we have. X y dash is the term we have. So x y dash in the sense z can be anything. Therefore, so this will be, okay, this can be considered as x y dash z, or this can be considered as x y dash z dash. Therefore, in these 2 places again we need to write logic 1, x y dash z. Where do we have 1 0 1? 1 0 1 is here. So here we need to write 1, and another value is 1 0 0. Here we need to write 1. In all other places we need to write logic 0. So the last one is f4. So similar to the previous, here the missing variable is z. Therefore this can be x y dash z, or this can be x y dash z dash. Similarly, this can be x dash y dash z, or this can be x dash y z. So 1 0 1 1 0 1. Where do we have 1 0 1? So here we should write logic 1. Next, x y dash z dash 1 0 0, that is 4. We need to write logic 1 here. Next is x dash y z dash 0 1 0. 0 1 0 is here. So here I should write 1. Next 1 0 1. 1 second. 0 1 1. 0 1 1 is 3. Okay. So 3. Yes. Okay. So these are the different Boolean functions and the respective truth table for those, okay, Boolean functions. So here I have represented logic 1s and 0s according to the values, or sorry, according to the expression. So what we have, okay. So this is about the Boolean function. After this we need to understand, okay, how to represent these Boolean functions using the logic gates. Okay, so implementation of Boolean function is the next topic to be discussed. Let us consider, okay, F1. So F1, if you observe, we have signal, okay, that is x, y, z. But if you observe, z is in its complement form. Therefore, whenever we draw a logic diagram, so we can have this kind of representation. So whether we require or not, signal can be considered both in original as well as complement form. So the function f1 can be implemented like this. So x, y, z dash. X, y, z dash. If these are given to an AND gate x, y, z dash, then so the output of the AND gate is the function f1. So this is the implementation of f1. Similarly, let us consider implementation of f2. So f2, what do we have? X plus y dash z. So we require, okay, one AND gate, one OR gate, and then one NOT gate. So we can, as I said, you can have this kind of representation, or we can go for another way, that is, so x must be given to OR gate, and another input to OR gate is the output of AND gate. Output of AND gate, input to AND gates are, AND gate is y dash z. Okay, y dash we have, therefore you can pass it through NOT gate and z can be given directly. So here we have x, y, z, here we have y dash, here I have y dash z, here I have x. So F2 will be equal to x plus y dash z. So this is another way of representation. Similarly, the F3 and F4 can also be implemented using the logic gates. Next, let us see simplification of Boolean function. So I have considered two examples. Okay. So now let us consider the first one. So first expression what we have is this one. Let me rewrite this expression. While rewriting, I am going to multiply this inside the bracket. A, B bar, C we have. Here I have A, B. So B into B bar is 0. Therefore, so this becomes 0 plus. So next we have A, B bar, C. Okay. So next, so if you observe, yes, so we can group these two. We have A as common, next we have B plus B bar C, next we have A bar C. So this can be written as B plus B bar, okay, because using distributive we can expand this like, so B plus B bar into B plus C plus A bar C. So next we have B plus B bar which is equal to 1. Therefore, so this becomes A into B plus A into C plus A bar C. So here I can take out C as common. So then within the brackets we will be having A plus A bar. A plus A bar is 1. So we have A, B plus C. Okay. So A, B plus C as the final answer. Let us look into the next example. So here, so if you observe in the first step, so we have x bar, y bar in all these three terms. There is a common factor in all the three terms. Let us take out x bar, y bar. Okay. So here we have z bar plus z bar plus 1 plus the last term we have is x, y bar. So here we have z bar plus z bar. So we know that x plus x is equal to 1. Therefore, so this will be here we have z bar plus z bar. We know that x plus x is equal to x. Therefore, so we will be getting z bar for this. Okay. Again here we have z bar plus 1. We know that any variable plus 1 will be 1 because this is OR operation. So whatever may be the value for z bar we get. So here since we have 0 or 1 or 1 or 1. So the possible values for this expression are 0 or 1 or 1 or 1. So in both the cases the result is 1. Therefore, so any variable plus 1 is nothing but 1. Okay. Plus x into y bar. So here we can take out y bar as common. So in the first term we have x bar and in the second term we have x. So we know that x bar plus x is 1. Therefore, so the answer for this, the simplified expression for the second one is y bar, whereas for the first one we have ab plus c. Okay. So this is about the simplification of Boolean function. In order to reduce the number of literals present in the given expression, so we can use the algebra to reduce. We can use Boolean laws and postulates. We can use the theorems in order to reduce these expressions. Now let us understand how to take the complement of a given function. Next topic we are going to discuss is complement of a function. So in order to obtain the complement, what we are supposed to do? So we are supposed to replace 1 by zeros and zeros by 1. Complement can also be obtained by using De Morgan's theorem. Now let us consider, as an example, let us consider f is equal to x, y, z dash. So this example we have taken in order to understand what is the Boolean function. So now let us take the same expression for the Boolean function f is equal to x by z dash. So in this case, okay, now to get the f dash of this, that is complement of f, let us see so how to use the De Morgan's. So we know that, okay, De Morgan's for two variables is written like this. So if we have complement of a product, that can be written as complement of or the sum of complement of the individual variable. On the other side, if you have a plus b whole dash, then this can be written as and between the complement of these variables. Okay, yes. Now, so as I said, in order to take the complement, we are going to use De Morgan's theorem. So we have, okay, so we have to expand this using the De Morgan's theorem, which I have written here. Yes, now f dash is equal to, yes, x dash plus y dash plus z double dash we get. So we can write it as z. So this is f dash. Therefore, so complement of any function can be obtained using the Boolean function. Okay, so we can consider one more example. Next example I have considered is, okay, this one. Let us consider the first expression, okay, f1 is equal to x dash y z dash plus x dash y dash z. So in order to find out the complement, so we need to, okay, consider this f1 dash x dash y z dash plus x dash y dash z whole dash. Okay, yes. So let us, so first we have plus here, so complement of individual term, plus becomes dot, then x dash y dash z whole dash. Yes, so here again we need to use De Morgan's theorem. Okay, another time. So x dash we have here, so x dash, again if you can take the complement, that will result in x. So since we have AND operation, so that will be changed to OR operation. Next we have y dash, next z. Okay, this is first term, and second term is x plus y plus z dash. So this is the complement of a function. Next we have f2. So f2, let us consider, okay, here itself we have, so let me, okay, take the complement of this. So complement of this, if you want, you can multiply x into this and then take the complement, or else you can retain as it is and then take the complement. f2 dash, okay, is equal to x dash, okay, then here we have dot, that will become plus. Next we have the second term is entire this one, okay, whole complement. Yes, again one more time we need to, okay, use De Morgan's. So first term dash dot, second term dash, next f2 dash is equal to x dash plus y z, okay, so sorry, so y plus z, x dash plus y plus z into y dash plus z dash. So that is the complement. So you can use the De Morgan's theorem any number of times in order to obtain the complement of a given function. So this is about the complement. We have discussed what is a Boolean function, then we have discussed how to, okay, represent the Boolean function into a truth table, okay, then we have understood so how to implement a Boolean function using basic gates. After that, so we have, okay, discussed about the simplification and then the complement of a Boolean function. In today's class, let us learn about logic operations. So here I have already listed the logic operations. So if you consider there are two variables, then it is said that the number of possible operations what we can have is equal to 2 to the power 2n. So then if n is equal to if n is equal to 2, then this becomes 2 to the power 2 into 2 which is equal to 2 power 4 which is nothing but 16. Therefore, so if there are 2 variables, then the number of possible operations are 16 operations. Now let us see, okay, and understand, so what are the different possible combinations, okay, what are the different possible operations we have, okay, when we have 2 variables in logic circuits. So here I have already written the input combinations, possible input combinations. Since we have 2 inputs here, so the possible combinations are 0 0, 0 1, 1 0 and 1 1. And now let us write, okay, the output logic values, okay, the corresponding columns. I have written operator symbol as well as I have written Boolean function already. Let us see, okay, according to the Boolean functions, let us, okay, write the or enter the output column. Yes, now if you observe, so in the first column I have written the Boolean function as f naught is equal to 0. So it is nothing but the values what we have for f naught all are equal to 0. So it is a constant 0 we have on f naught. So this is how we write, okay, the first function, so which is possible. Next function, if you observe, f1 is equal to x into y, the logic symbol or the operator, okay, what we have is dot. Therefore, so it indicates that it is a AND operation, logical AND operation. In this case, so we have, okay, the truth table which is written like this. So this indicates that it is a logical AND operation. So AND is 1, the output of AND gate is 1 only when both the inputs are equal to 1. So for all other combinations the output is equal to 0. Okay. Now see here I have written, so the function name what we have for f naught is null, okay, and this is AND. Now let us see, so what is f2. So f2 what we have here is f2 is equal to x into y dash. This is the Boolean expression. So according to this let us write the values for f2. So x into y dash, it is called as implication. Sorry, it is called as inhibition. F2 is equal to x into y dash, it is called as inhibition. Now let us write, okay, so what is the equivalent value to this f2 here. So f2 is x into y dash. Why we need to take the complement? So complement 1 0 1 0, later I will erase this. So now let us, okay, find the AND between this x and y dash. So here we have 0 1, so AND operation is 0 and output is 0, 0 0 and output is 0. Here we have 1 and at last we have 1 0, okay, which is again 0. Okay. So this is the output for this Boolean function and it is called as inhibition. Now, so let us see the next possible function. Next possible function is f3 and the Boolean expression what I have written for f3 is x. So now it is nothing but just we are transferring the value of x to the function, okay. Therefore, we need to just copy x from, okay, the input side. Yes, 0 0 1 1 is x what we have. Yes, now this is just called as transfer of, okay, one of the variable to the output. Next, let us see what I have written for the Boolean function. So I have written x dash y as the next function, x dash y. So now let us consider x dash here 1 1 0 0 and between these two will result 0 1 0 0 will result in this, okay. So 0 1 0 0 value. Now this is also called as inhibition. Okay. Next, see fy is equal to y. This is the next Boolean function we have. So just transfer y, okay, to the function, to the output. So here we call this as transfer, okay. Yes. Next, so f6, the symbol what I have written, okay, is XOR, or if you just, okay, see the expression x y dash plus x dash y is nothing but XOR operation, exclusive OR operation between the x and y, okay. In that case So for 0 0 we will get 0, and okay, for 0 1 the output is 1, again for 0 1 0 the output is 1, and for 1 1 output is 0. So for this, okay, we are going to get logic 1 whenever the output, whenever the inputs are different, okay. Then let us, okay, write the name as exclusive OR. Okay. Now let us see the next operation. Next operation is F7, which is equal to x plus y. So this plus is nothing but logical OR operation. Therefore F7 can be written like this: 0 1 1 1. So when we have both the inputs as 0, for other than this combination, for all others we have the output which is equal to logic 1. So this or this, since we are taking OR between the two variables, so we are having logic 1 for the 3 combinations except for the first one. So this is nothing but logical OR operation. Next F8. Okay, let us see the next function F8. So here all of you see x plus y whole dash we have. So previously we had x plus y. So now we need to take the complement of this. So complement of this is nothing but 1 0 0 0. Therefore, so this can be written as, okay, or called as NOR. The name for that function is NOR. Okay, it is not of OR. Yes. Next, if you observe, so the expression what we have, the Boolean function what we have is xy plus x dash y dash. So this is nothing but exclusive NOR. Okay, it is nothing but exclusive NOR. So sometimes it is called as equivalence. Okay, so we can call this as equivalence or exclusive NOR operation. So it is opposite to the XOR operation. Here we have the, okay, the entry for F6, which is a exclusive OR operation. Let us take the complement of this. So if you take the complement, so the output is 1 0 0 1. Next, let us see next function, that is, okay, F10. F10 equation what we have for F10 is y dash. Y dash is nothing but complement of y. So complement of y is 1 0 1 0. So we can write the function as complement. Next, let us see the next function. Next function what we have is F11. F11 here, so see the expression what we have, x or y dash. X or y dash. Let us write y dash, x or y dash. If I, okay, apply logical OR between x and y dash, so I will get 1 0 1 1 1 0 1 1. Okay, see here. So logical OR between these two. 0 1 is 1, 0 0, 0 or 0 is 0, 1 or 1 is 1, 1 or 0 is 1. Okay, yes. So that is called as implication function. Okay. Next, so the next function we have is F12. F12 is x dash. X dash is nothing but complement of x. Complement of x is 1 1 0 0. So here the name is, okay, complement. Next we have F13. So F13, okay, F13 is x dash plus y. X dash plus y. It is also called as implication. Okay. Now let us consider x dash. So all of you see, we have 1 or 0. 1 or 0 is 1. 1 or 1. 1 or 1 is 1. Next we have 0 or 0. Okay. Next we have 0 or 1. This is the implication function x dash or y. Yes. Now let us see the next function. Next function we have is F14. So F14 expression we have is x into y whole dash. X into y, we have here the as and operation. So the complement of and operation. So the truth table or the output value will be complement of and. So 1 1 1 Okay, so we have 0. So if you observe, we have 0001 as the entry here, therefore so complement of this is 1110. Okay, and the operation is NAND operation. We call this as NOT plus AND, so which is nothing but okay NAND operation. Now the last function what we have is, see, I have written F15 is equal to 1, therefore so here we have a constant 1, or we call this as identity. Okay, so this is about the 16 possible functions what we have, and their okay the operator symbols and Boolean functions and the names. So here we have a dot, here we have a slash, okay, etc. So you can observe the different symbols what we use okay in logic operations. So now out of this, if you observe, these 16 operations can be categorized into 3 categories. So one first category is a constant. Okay, we can classify this into 3 categories. First is constant 0 or 1. Second category is inhibition. Inhibition and implication function. Okay, so these are 2 functions, 2 operations. Here we have totally 4 operations. Next, the third category is 10 operations, which includes AND, OR, NAND, NOR, then we have exclusive OR, exclusive NOR, complement, yes, and we have transfer. Okay. So these are the 16 possible combinations when we consider 2 variables. Okay, and as I said, all these can be classified into 3 different categories. So first one is constant 0 or 1, next is inhibition and implication functions, and the last category includes all other logic operations. Now we are not going to use okay all these operators. Instead, let us see so which are the commonly used operations or operators, because if you observe the equations whatever I have written, the Boolean functions whatever I have written, all these can be implemented or represented by using AND gate, OR gate and NOT gate. Using basic gates we can realize any of these expressions. Therefore, so we are not going to use all these operators, all these 16 operators or operations. Instead, so we will be using only 7, we will be representing only 7 operations in the form of gates. Let us see which are those, and so let us understand what is the logic symbol or the logic gate symbol for respective operations, as well as let us see the truth table for individual gates. Next, let us see the logic gates. So we have 7 logic gates. Let us AND, okay, OR, NOT, buffer. Next we have, before this let me write NAND, NOR, exclusive OR, exclusive NOR. Okay, I said there are 7 logic gates. So along with that, the frequently used one of the component in digital circuit is buffer. So let us see what is buffer and what is the symbol used for buffer, and okay, the truth table for buffer. Now I have written all the operations, okay, and the commonly used logic gates. So these are the out of 16 operations. So these are the 7 operations which we are going to, okay, see now. Now let us consider the first gate, which is AND gate. AND gate symbol, logic symbol used for AND gate is this one. So let us consider XY as input and F as output. So if that is the case, the truth table. So here is the logic symbol, okay, the first whatever I have written is the logic symbol. Next let us see the truth table for the same. Truth table. So we have XY as input and F as output. So possible combinations are so since we have 2 inputs, so we will be having 4 combinations, and output we have already discussed. So output is logic 1 for only the last combination, in the sense when both are logic 1, that is both the inputs are logic 1s, then the output is 1. Next gate we have is OR gate. For OR gate, the logic symbol what we have is this. So X and Y are inputs, F is output, okay. So the truth table for OR gate is, let us consider the same, okay, inputs here and output. So if you observe the OR gate operation, so we have already discussed. So for the possible combinations we have, so except for the first combination, for all others we have the output as logic 1. Next is NOT operation. NOT is a unary operation, so it is applied only to a single, okay, variable. It can be used on only single variable. So now we have X as the input, and let us consider F as output. In this case, so we have, since we have only one input, possible combinations are 0 and 1, and output is 1 and 0. It is a complement. See, so here I have missed a bubble actually. So this is the NOT gate symbol. We have a triangular symbol with a bubble at the output side. So we have X, okay, so which is having a value 0, 1, and complement of X is, okay, the value for F. So 1, 0 is the value. Next we have buffer. So buffer symbol is this, without bubble, okay, it is same as the NOT gate symbol, but we are not going to use bubble at the output end. So this is the buffer, okay. So as the name itself is indicating, it is used to store the value temporarily. So if I give 0, output is also 0. If I give 1, output is also 1. So this is the truth table for a buffer. Next we have NAND. Symbol for NAND is AND, okay, followed by AND gate symbol, followed by a bubble at the output end, okay. X, Y, let us consider F as output. Possible combinations, F is complement of AND, we get 1, 1, 1, 0 as the value. Next we have NOR operation. NOR symbol is same as OR, but we need to use bubble at the output end. So this is the symbol of NOR gate. So we have X, Y and F, 0, 0, 0, 1, 1, 0, 1, 1, and so output is complement of OR. Complement of OR is nothing but, so for the first case you will get 1, for all other combinations it is 0. So this is the truth table for NOR. Next gate what we have is exclusive OR operation. Exclusive OR, okay, this is the symbol we use. You can extend this. This is the symbol we use. Let us consider XY as input and F as output. So truth table, it is exclusive OR operation. So when the inputs are same, output is 0. When the inputs are different, then output is logic 1. So this is the truth table of exclusive OR gate. At last we have exclusive NOR gate. So which is represented like this. One, 0, 0, 1. It is the complement of exclusive OR. Therefore, this is the truth table of exclusive NOR gate. So this is about the basic gates what we have, as well as along with the basic gates we have other operations also. And as I said, so buffer is an addition to the logic operations what we just previously discussed, and it is nothing but a transfer operation, right? So buffer is nothing but transfer operation. We can consider it as one of the operation itself. Yes, these are the 8 different operations. After knowing about the gates what we have in the digital circuits, okay, in digital electronics, now we need to understand so how to extend the number of inputs. So if you have 3 variables, then how to, okay, so represent a 3 variable AND gate. Can we represent, or do we have 3 variable or 4 variable AND gates, OR gates, etc. that we need to understand. So if you consider AND and OR operations, those can be extended to any number of inputs, because so in order to extend we have a rule, that is it must be associative and it must be commutative. So if you consider AND operation and OR operation, both are associative and okay. So if you consider OR operation, so OR can be written like this. It is OR even AND operation, both are associative and commutative. So if an operation is both associative and commutative, then it can be simply extended to any number of inputs. Therefore, so we can have 3 input AND gate, 3 input OR gate, 4 input AND gate, 4 input OR gate, etc. And if we consider NOT operation, so we know that it operates on single variable, so it cannot be used for multiple variables. So now let us understand whether we can use or extend the number of inputs to NAND gate, NOR gate, XOR gate and exclusive. Next let us see logic operations. Okay, next let us see the logic gates. So we have 7 logic gates. Let us AND, okay, OR, NOT, buffer. Next we have, before this let me write NAND, NOR, exclusive OR, exclusive NOR. Okay, I said there are 7 logic gates. So along with that, the frequently used one of the component in digital circuit is buffer. So let us see what is buffer and what is the symbol used for buffer, and okay, the truth table for buffer. Now I have written all the operations, okay, and the commonly used logic gates. So these are the out of 16 operations, so these are the 7 operations which we are going to, okay, see now. Now let us consider the first gate, which is AND gate. AND gate symbol, logic symbol used for AND gate is this one. So let us consider XY as input and F as output. So if that is the case, the truth table, so here is the logic symbol, okay, the first whatever I have written is the logic symbol. Next let us see the truth table for the same. Truth table, so we have xy as input and f as output. So possible combinations are so since we have two inputs, so we will be having 4 combinations, and output we have already discussed. So output is logic 1 for only the last combination, in the sense when both are logic 1, that is both the inputs are logic 1s, then the output is 1. Next gate we have is OR gate. For OR gate, the logic symbol what we have is this. So x and y are inputs, f is output. Okay. So the truth table for OR gate is, let us consider the same, okay, inputs here and output. So if you observe the OR gate operation, so we have already discussed. So for the possible combinations we have, so except for the first combination, for all others we have the output as logic 1. Next is NOT operation. NOT is a unary operation, so it is applied only to a single, okay, variable. It can be used on only single variable. So now we have x as the input, and let us consider f as output. In this case, so we have, since we have only one input, possible combinations are 0 and 1, and output is 1 and 0. It is a complement. See, so here I have missed a bubble actually. So this is the NOT gate symbol. We have a triangular symbol with a bubble at the output side. So we have x, okay, so which is having a value 0, 1, and complement of x is, okay, the value for f. So 1, 0 is the value. Next we have buffer. So buffer symbol is this, without bubble, okay, it is same as the NOT gate symbol, but we are not going to use bubble at the output end. So this is the buffer, okay. So as the name itself is indicating, it is used to store the value temporarily. So if I give 0, output is also 0. If I give 1, output is also 1. So this is the truth table for a buffer. Next we have NAND. Symbol for NAND is AND, okay, followed by AND gate symbol, followed by a bubble at the output end, okay. X, Y, let us consider f as output. Possible combinations, f is complement of AND, we get 1, 1, 1, 0 as the value. Next we have NOR operation. NOR symbol is same as OR, but we need to use bubble at the output end. So this is the symbol of NOR gate. So we have x, y and f, 0, 0, 0, 1, 1, 0, 1, 1, and so output is complement of OR. Complement of OR is nothing but, so for the first case you will get 1, for all other combinations it is 0. So this is the truth table for NOR. Next gate what we have is exclusive OR operation. Exclusive OR, okay, this is the symbol we use. You can extend this. This is the symbol we use. Let us consider xy as input and f as output. So truth table, it is exclusive OR operation. So when the inputs are same, output is 0. When the inputs are different, then output is logic 1. So this is the truth table of exclusive OR gate. At last we have exclusive NOR gate. So which is represented like this. One, 0, 0, 1. It is the complement of exclusive OR. Therefore, this is the truth table of exclusive NOR gate. So this is about the basic gates what we have, as well as along with the basic gates we have other operations also. And as I said, so buffer is an addition to the logic operations what we just previously discussed, and it is nothing but a transfer operation, right. So buffer is nothing but transfer operation. We can consider it as one of the operation itself. Yes, these are the 8 different operations. Now after knowing about the gates what we have in the digital circuits, okay, in digital electronics, now we need to understand so how to extend the number of inputs. So if you have 3 variables, then how to, okay, so represent a 3 variable AND gate. Can we represent, or do we have 3 variable or 4 variable AND gates, OR gates, etc. that we need to understand. So if you consider and OR operations, those can be extended to any number of inputs, because so in order to extend we have a rule, that is it must be associative and it must be commutative. So if you consider AND operation and OR operation, both are associative and okay. So if you consider OR operation, so OR can be written like this. It is OR even AND operation, both are associative and commutative. So if an operation is both associative and commutative, then it can be simply extended to any number of inputs. Therefore, so we can have 3 input AND gate, 3 input OR gate, 4 input AND gate, 4 input OR gate, etc. And if we consider NOT operation, so we know that it operates on single variable, so it cannot be used for multiple variables. So now let us understand whether we can use or extend the number of inputs to NAND gate, NOR gate, XOR gate and exclusive NOR gate. Okay. As I said, both AND operation and OR operations can be extended to multiple inputs because both satisfy both associative as well as commutative law. Therefore, it can be extended to any number of inputs. So, if you consider the NAND and NOR operation, these two are commutative. They satisfy the commutative law but are not associative. So now let us see the non-associativity of the NOR operation. So if we consider the NOR operation, so we can write this as X NOR Y, okay, NOR Z. It is not equal to X NOR Y NOR Z. Okay. Now let us consider the first one, X NOR Y NOR Z. If X plus Y whole dash plus Z whole dash, right. So this can be expanded like this, X plus Y whole dash, okay. So if I use De Morgan's, so here I have complement, one complement already again, okay, we will get double dash into Z dash, which is equal to X plus Y into Z, which is nothing but X into Z plus Y into Z. Now let us consider the RHS. In RHS we have X, okay, NOR Y NOR Z, which is equal to X plus Y plus Z, okay, dash whole complement, okay. Yes. Now, so if I expand this, X dash dot Y plus Z. So if I multiply, so I get X dash Y plus X dash Z. Now, so if you observe, so we have X into Z plus Y into Z here. So whereas in this case on the RHS we have X dash Y plus X dash Z, okay. Both the functions are different. Therefore, so NOR is not associative. So now we can extend or we can include multiple inputs even for NAND and NOR gate if you just change slightly the way in which we write. So instead of writing like this, we can write like this, that is for 3 inputs, we can write like this, x into y into z whole dash. Instead of writing x for NAND we have this symbol x NAND, y NAND, z. Instead of this we can use this. Similarly for x NOR, y NOR, z for 3 inputs, we can write like this, x plus y plus z, whole complement. So now we can use the NAND as well as NOR gate, so for multiple inputs. So if you write like this, so XOR operations can also be extended to multiple inputs, but usually what do is we realize multiple inputs using the 2 inputs XOR gate. Say for example, if you have 3 input or 3 variable XOR operation, then so we realize like this. So first we give the 2 inputs to first XOR gate, the output of this will be given to the XOR gate, 2 input XOR gate. So the other input to this will be output of the first XOR operation will be given as 1 input, the other input will be the third variable, and here we will be having x XOR y XOR z, and here as I said we can have multiple input XOR operation and XNOR operations. So this is how we represent the 3 input XOR gate. Let me represent the output function as f. Similarly, if you consider the other gates, AND gate is represented like this, multiple input AND gate, and multiple input OR gate, multiple input NAND gate. I have considered 3 input for all these. So this is 3 input NOR gate. So this is how we can extend the number of inputs to each of the operations what we have except the NOT operation. This is about the logic operations, the logic gates and extension to multiple inputs. Thank you.